Hello, hello. Good morning, good evening to everyone who's joining in from different cities across the world. I am Vino. I work as a developer advocate at Snowflake, and today joining me is the product manager at Snowflake, Tim Sander. He's here to talk about all things automatic clustering, how to use automatic clustering to improve query efficiency, and when should you use it, and what's new with it. We know that automatic clustering has existed for a while now, but why are we talking about it today? So let's welcome Tim Sander onto the show. Hey, Tim, excited to talk to you.
Hey, yeah, it's great to be here again today, and I'm excited to share maybe a quick recap of automatic clustering and then share a lot of the new awesome updates that we've been working on over the past year.
Gotcha. Well, before we get into the updates, can we maybe, for some of us who may be new to automatic clustering, what exactly is it and maybe when I should use it?
Yeah, for sure. So I guess to start off, in general, in Snowflake, it's a product where there's not a lot you need to optimize, right? It generally will work pretty well for performance out of the box. So in a lot of cases, hopefully you don't need to use any of our advanced optimization features to manually tune performance. But when you do need to tune performance, automatic clustering it's the most common feature used. It's one of the oldest optimizations in Snowflake, right? That has existed since the beginning of the product. And it's also one of the most powerful ways to improve your query performance. So to start off, I'll talk a bit about the feature at a high level, and then we'll talk through an example of how it works. So we'll first jump to a really awesome blog that a member of our engineering team wrote a few years ago. And it was published back in early 2022, but obviously clustering has existed for a while within Snowflake, so all this information is still relevant. So I'd recommend reading through this blog up here in case you wanted to learn more. And at a high level, what automatic clustering does in Snowflake is it maintains basically your data ordering across all of your micropartitions to allow for efficient query performance by allowing those queries to scan only the minimum amount of data required. In general, most of the time queries are expensive and run a long time in Snowflake. It's because the queries needed to scan a lot of data. And the purpose of clustering, the goal of clustering, is to make sure your data is stored across your micropartitions in such a way such that your queries can scan as little data as possible. So in this Medium blog post, Ryan, the person who wrote this, shared a great example of how clustering works and had a fictional data set where we had 4 columns in a table broken down into micropartitions. So I made this little example into an animation and slides. So I wanted to talk through that together so we can better understand how automatic clustering works. So in this example here, we have this table with 4 columns: a type column, name column, country column, and date column. And there's, I think, about 20 or so rows, 20, 25, 24 rows within this table. And what we'll do is we'll take this table, which of course is very tiny. Most of the time, tables in Snowflake are going to have many, many millions or billions of rows. But we'll take this 24-row table and break it down into 4 micropartitions. Now, again, the way clustering works is it helps you improve query performance by optimizing how your data is ordered across your micropartitions. So in this particular table, we only have 4 micropartitions. But of course, typical Snowflake tables would have many more than 4. What we can do is take each of the rows in our table and basically store it on our micropartition. So this row, for instance, would be stored within micropartition 1. This would be stored within micropartition 2, and so on. Now, the secret sauce to making all of this work really well is this metadata that we keep internally on each of your micropartitions, so that when our query engine runs and decides whether it needs to scan each of these micropartitions, it can first consult this metadata on each of the micropartitions to decide if that micropartition has any possibility of containing the data that the query is filtering to and looking for. So for instance, on micropartition 1, we know for the date column, the minimum value is 11-2, which in the American date notation is November 2nd. I know like in other places that would be February 2nd. So apologies if this is very, I don't know, very, very specific to how I'm familiar with dates, but this is denoting November 2nd with a min November 2nd, max November 2nd. The date column here is a min of November 2nd and a max of November 3rd, and so on. So if we ran a query, for instance, that filtered to where date was equal to November 2nd, we would know that we would only need to go and scan 3 of the micropartitions. This 4th one here, since the minimum is November 3rd and the maximum is November 5th, we would know that this micropartition has no possibility of containing the results of this query, so we wouldn't need to go and scan it at all. Now, for instance, if we filtered on the name column, right, we have these min and max values for each column for name. If we filtered to where name was equal to B, how many micropartitions would we need to scan?
Well, oh yeah, okay.
We need to scan them all, right? Because what the query engine would say is, oh, well, is B within this range, right? Can we use this metadata to conclude whether a micropartition has no possibility of containing this data? And in each of these cases, B is within the range of these values, so we would scan them all. And of course, clustering is the feature that you can use to optimize how the data is stored across these micropartitions to make this min and max range narrower. So for instance, if we cluster this table by name, what we do is basically sort all of this data across all of the micropartitions by name. So if the word clustering is confusing, you can almost in your mind replace it with order by. That's kind of how you would want to think of it. We're basically going to order the data across all the micropartitions by name. And of course, when we do that, if you pay attention to these metadata values here, they change, right? And they become a lot more narrow, a lot more specific, right? So when we sort the data by name, now suddenly instead of a wider min and max range, the min and max range are a lot narrower on each of the micropartitions. So when we come and run this query again, we can scan basically fewer micropartition. Actually, I realized I quoted this example wrong. It should be 1 and 2, not just 2. I made the example too quickly. So we would be able to just scan these 2 micropartitions and avoid scanning these entirely, because name equals B doesn't exist at all within the range C to X and Y to Z. So that's what clustering does, right? We're basically optimizing how your data is stored across your micropartitions so that we can scan as little data as possible.
Gotcha. So then when would I actually cluster a specific table? Because in this example that you showed, we didn't initially need to, but then eventually, because we are querying using the name field as one of the keys, we decided to cluster, right? So then in a real example, like in a real-time world, when would I think about clustering my table?
Yeah, it's a great question and a really great point. And it really comes down to how often is your table accessed in that specific way. So you can see here that we ran a query that filtered by date and a query that filtered by name, for instance. And in each of these cases, there was a potential for clustering to improve performance quite a bit and potentially save on query costs by allowing you to go and filter out micropartitions that you knew you didn't need to scan. And whether or not you want to use clustering really comes down to how long these operations are taking without clustering and how frequently they are. If they're incredibly frequent, obviously, then clustering has a higher potential impact. Additionally, it's good to keep in mind that you might get really good performance out of the box, even without clustering. In this example here, we were able to get some pruning even without using automatic clustering, because just based on how the data landed in Snowflake, we had min and max values on each of our micropartitions that were reasonably useful for pruning. So you only want to use automatic clustering when you already encountered a performance problem. If you use it proactively, you may go and optimize your tables when it actually isn't really all that necessary. And you might get good performance out of the box and never even need to use the feature.
Got it. So then in the last slide, when you were showing how after the clustering is enabled on a specific table, how the data is sorted in by a specific key, right?
Mm-hmm.
But what happens when we write to that table now?
Yeah, it's a great question. So what the automatic clustering service will do is keep the data clustered by your specified key. In other words, keep it ordered by your specified key automatically without any kind of action required on your end. So you'll pick the clustering key, run a SQL statement to cluster by those columns or a particular column, and Snowflake will automatically maintain that for you without any kind of action required.
Gotcha. That's very cool. In that case, is it actually clustering or like sorting these in the background? Does that affect the response rate for the queries while it is doing clustering under the hood?
It's done completely in the background, so it won't interfere with any of your queries. Or if you, let's say, were writing new data, it wouldn't do any kind of system lock or anything like that to prevent you from doing so. So absolutely no impact to read or write availability or read or write performance.
Okay, so that's very cool. So I can have a table, and if I decide to have, automatic clustering enabled by a specific column, Snowflake will do that for me, so I don't have to worry about manually, enabling the clustering every time I update or insert new data. Also, I don't have to worry about performance or like responsiveness to the query at all. Everything sounds great. Now, we understand what exactly clustering is and when I would use it.
Mhm.
But tell me, why are we talking about it today? What's new? What's happening?
So I'd love to dive into some new stuff we have for automatic clustering. And of course, automatic clustering is really the most popular and common way to tune query performance. So it's a feature that we're investing in quite a bit at Snowflake. And over the past couple of years, our most common request for clustering has been to build estimation functionality for the cost. Oftentimes, picking the best cluster key requires a bit of trial and error, and
Mhm.
changing your cluster key obviously requires changing how the data is stored. So it can be an expensive operation. So a lot of customers have asked for, hey, can you give us some sort of functionality to estimate the costs without us needing to go and actually incur them? So we built this for search optimization a few years ago, and we're super excited to announce the public preview of a cost estimation function for automatic clustering now as well.
Very cool. So before I even enable automatic clustering, I can maybe, run around try around with different keys and see what the cost is going to be and then commit to enabling the clustering.
Exactly. Yeah. You could compare costs for different potential keys. You can try to understand if it's going to be, because in some cases, clustering can be a lot cheaper than you'd expect. The cost really depends on how much and how often the data changes in the table that's clustered. So in some cases, you could be pleasantly surprised by the cost. It could be a lot lower, or in some rare cases, a lot higher than you'd think. So this gives you a really good understanding of what to expect. So you can run this function and kind of know, are you getting into something that's cost you a handful of credits, or will it cost you more?
Got it. So then how do I go about running these cost estimation functions? Is there like specific, I don't know, best practices around it? How long does it take it to run? Can I just play around with all the keys in my table and keep running the cost estimation functions? Because sometimes when you don't know what are the right keys, I might as well brute force it and see all the keys. Just tell me where should I start with to estimating these costs?
Yeah, great question. So it's a system function that you can run. So it works just the same way as all the other system functions in Snowflake. And what you'll want to do is in the system function, give the table name and then give your potential clustering key that you want it to cluster by.
Okay, so that is fairly straightforward. And do you know how long it takes? What warehouse should I use or anything at all?
Yeah, it should take you under 10 minutes. Hopefully just a few minutes, and we're always working on improving the performance here. But
Mhm.
vast majority of the time, it'll finish in under 10 minutes. And it actually doesn't matter what warehouse size you use. So if you used a triple XL or you use an extra small, it'll have the same performance. So for that reason, obviously, we strongly recommend just use an extra small size to calculate this.
Fair enough. And also, as with anything else, it says it's just an estimate. So how can I be sure that how close is it going to be to the actual cost of it?
Yeah, great question. So we break down the estimate into two categories. There's the initial estimate, and this is the initial cost to recluster your data by your specified key. And obviously, we express this in credits. So this value is the credits, where if you were to change your clustering key, how much it would cost to get your data clustered by that new key. And obviously, this is just dependent on how different your data is now from the state that it would need to be in to be considered well clustered by that new key. So in this case here, if we were to change the clustering key to cluster by the tenant ID, it would cost us 98 credits to go from the current state of the table to this new key on tenant ID. We also have a maintenance cost estimate, which shows once this data is in a well-clustered state, how much will it cost to maintain it? How much will it cost to keep that data well-clustered over time? And this depends obviously on how much the data changes in that table. So in this case, it would cost us 10 credits to keep the data well-clustered by tenant ID once it's in that state. In some cases, the initial estimate we're able to return every time when you run this function. In some cases, though, just based on your table's past DML history, past history of like writes and updates and that kind of thing, we might not have enough data to estimate the maintenance costs. So in that case, we would still return an initial cost. So if we return the initial cost, that'll give you a sense of what kind of investment would you need to go and recluster the table by this new key. So for instance, if we returned an initial cost of 98 credits and didn't return a maintenance cost, or perhaps you were nervous about the maintenance cost and wanted to validate it first, this will help you understand what's the investment that you'd be making in doing experimentation and changing the clustering key. And for the most part, this initial estimate is going to be biasing towards an overestimate. We certainly want to be safe when providing costs to you for this. So we actually phrase it here as an upper bound. So most of the time, the cost is going to be less than this. And in some cases, it'll actually be much less than this. But that's the kind of the rough upper bound costs that you'd want to keep in mind when and to expect when reclustering your table.
Got it. And also when I don't get the values for the maintenance side of things, is it fair to say that the maintenance costs are going to be a fraction of the original one-time cost? So that should give us an estimate, even if I don't have it, if it's a new table.
They could be, but they may not correlate. Really, the one-time cost, the thing that affects it is how well clustered is your table right now with respect to this new clustering key. So if you had, let's say, a clustering key that was very, very different, it's possible that this number could be very high. But if your table wasn't changed that much every day and your data stayed about the same, it's possible that this number could be really high, but this could be really low. The reverse is also possible. It's possible that, for instance, let's say we were currently clustered by tenant ID, and then we wanted to recluster the table to something like company name. Tenant ID and company name, the values probably correlate, right? They're probably the same. Like Snowflake, I don't know, its tenant ID might be ABC123, right? Let's say you had like Bob's Coffee Shop, just to come up with the name of a fictional business. Maybe that's tenant ID is ABC1234, right? For example. So in these cases, tenant ID and company name would be the same. So if we were to, let's say, recluster our data by company name instead of tenant ID, it's possible that this value could be pretty low because there's not much new work to be done to recluster the data. But then the maintenance cost would depend on how much new data is coming to this table, how often do we need to rewrite your micro-partitions, and that's what would drive that higher.
Okay, yeah, so that's helpful. They're not necessarily correlated. It really depends on currently under what keys have we enabled automatic clustering and what are we estimating it for. So that should help.
Exactly, yeah, great questions.
All right, so now that we've talked about when to use it and how to use these cost estimate functions, do you want to maybe tell us how it exactly works under the hood a little bit?
Yeah.
Internal improvements, perhaps?
Great question. So this is an area actually we've been investing in quite a bit over the past year. And this is something that's sort of invisible, right? When you use Snowflake, things get faster, but oftentimes you're not doing a direct before and after to compare things like query performance over time or automatic clustering costs over time. But in the past year, we've invested in this quite a bit for automatic clustering. And we're super pleased to announce that over the past year, we've released a slew of improvements that in aggregate have improved clustering costs substantially. Now, we can kind of bucketize these improvements into two categories. The first, and this one actually was by far the most impactful, is faster reclustering job execution. So when you cluster a table, all you need to do is run that simple SQL statement that we had showed here. right, to recluster the table, right? You're on this alter table cluster by statement. Internally, when you run that, what Snowflake is going to do is figure out, okay, the user wants to sort the data, cluster the data by these particular columns. How can I do that most efficiently? And we go through and look at all of your existing micropartitions and break that work down into many smaller, we call them jobs. Basically, there are many smaller internal queries that we run to go and modify your data and rewrite all of your micropartitions so that they're better sorted. And recently, we released an improvement that made each of these jobs smaller in size so that in aggregate, they could better utilize resources internally for when they're run. In other words, they could better utilize our internal compute resources to run these jobs. And we just went and passed those savings, obviously, directly onto you, the customer. And the result is that automatic clustering runs a lot more efficiently, and in some cases even runs a little bit faster as well. So the costs will be quite a bit lower. And what was pretty cool to see is there were some customers when we went and looked at the data that actually saw their costs go down by more than 30% for automatic clustering. So if you were to look at it before and after this change, you would see a pretty dramatic improvement, which is awesome.
Very cool.
The other things we invest in is into our actual reclustering algorithm. In other words, how we decide which micropartitions we want to recluster and when we kick off those jobs, those internal queries to go and recluster that data. And we improve the efficiency here in two areas. The first is in workloads that have a high volume of concurrent queries which modify data. So in these cases, what we've done to make these more efficient is we've focused on basically your micropartitions that we think we can most efficiently cluster, and we focused on those, and ones that we don't think we can efficiently cluster, we kind of let be for a little while. And by focusing on the workload that we can more efficiently cluster, which most of the time is data that's slightly older, we're able to dramatically lower cost and improve the efficiency of the automatic clustering service. We also have improved how automatic clustering works with Snowpipe. Previously, automatic clustering and Snowpipe did independent background micropartition consolidation. So basically, they each independently went and optimized micropartition size. Now we've made it so these two services work together. They're not duplicating the work, and we basically transferred that work just to automatic clustering. So if you're using Snowpipe and you're using automatic clustering, it got even more efficient, and a lot of that micropartition work will be fully handled by the automatic clustering service so that there's no inefficiency there, and it'll work kind of all within one service that handles the micropartition consolidation.
Got it. I have a question here. So when I am ingesting a lot of these small files, so to speak, into Snowflake using Snowpipe, it does look like when I use Snowpipe in combination with automatic clustering, I may be able to work around this small file problems. Would that be a fair assessment?
Yeah, that's right. It'll be just handled by the automatic clustering service. You won't need to tune anything on your own, and automatic clustering will go and optimize any small files created.
Gotcha. That's very cool.
Yeah. And the other thing I'll touch on is actually, and this is actually maybe that question is a good tangent to the last topic I wanted to talk about, which is how Snowflake optimizes your micropartition size. And I think I've been a little sloppy. I've used the word file sometimes, micropartition size other times. Think of these as interchangeable. It's just the word we use internally to describe micropartitions, but they mean the same thing. And if you use automatic clustering, automatic clustering is going to be the service that will go in and optimize your micropartition size so that you get good query performance. And a lot of other systems, you might have to run specific commands, right, to go and clean up small micropartitions or maybe optimize them and optimize to a specific size or things like that. But if you use Snowflake and you use automatic clustering, the automatic clustering service will just do all this automatically, and there's nothing you need to pay attention to or tune. Now, one thing we don't highlight as much is that if you don't use automatic clustering, this is still handled automatically by Snowflake. And we've highlighted that in this blog here that you can read through on your own if you want to learn more. But at a high level, there's two ways that Snowflake goes and optimizes the micropartition size. One is foreground micro-partition consolidation. So with that, when you run copy, inserts, merges, or other DML operations in Snowflake, within that DML operation, we'll actually automatically go and do work to maintain an optimal file size. And then if that doesn't keep up and we still need to do additional micro-partition consolidation, we have a background service that runs automatically for no additional cost in the background. And if there's any kind of straggler small micro-partitions that we need to optimize, that will go and handle that automatically for no additional costs to the customer. So whether you use clustering or not, whether you have enabled the automatic clustering service or not, we will automatically go and maintain a file size within your tables that's optimized for good query performance. So unlike a lot of other systems, it's nothing you need to worry about, and you don't need to run any kind of specific commands to achieve that.
Got it. And just another question before we move on to the next section, which is when we started out, we said automatic clustering, or clustering in some sense, is about how we reorder the data in the table based on specific keys. We didn't touch so much about resizing the micro partitions. But looking at this now, when I say automatic clustering, is it one, reordering the data by the specific key so it's easy for the query to access or scan only minimal set of micro partitions? Two, does it also involve resizing micro partitions?
Yeah, so let's break that down into two parts. So the first part of the question, could you just repeat that first part? I want to make sure I answer that.
Yeah, okay. So the first part of the question is, we said clustering reorders or sorts your table data by the specific key you want to create the cluster on, which we all understand. But how is this resizing the micro partition connected to automatic clustering?
Great. Oh, I see. That's a really great question. So these operations are very closely related because when you're sorting your data, you're going to be rewriting a lot of your micro partitions, right? In Snowflake, when your micro partition data changes, what Snowflake does is it creates a new micro partition, right, with those updates and rewrites it. And when we're doing that work, it's an opportunity to also go and optimize the size of your micro partitions. So in the extreme case, if you had micro partitions that, let's say, had one row each on all of the micro partitions, it could be very expensive when you needed to query that data because we'll need to go and scan a lot of micro partitions. So the reason that these two kind of problems are both solved by the automatic clustering service is when we're going and we're rewriting your micro partitions anyway, when we're sorting your data, it's efficient to go and optimize the size and consolidate micro partitions at that time as well.
Got it. So when I enable automatic clustering on a table, I, as a user, am only asking for the data to be sorted by that specific key. But then the way Snowflake implements it under the hood, it also goes one level further, and while it is doing this sorting of data, it also does resizing of these micro partitions to make it, even more optimal.
Exactly. And if you don't use automatic clustering, we won't do that sorting for you, but we'll still go and automatically optimize the micro partition size.
Gotcha. That's very cool. So it's more like every time I run a query, I know how easy it is, but also it's super interesting to see how it is all being done under the hood from Snowflake's end.
Yeah, there's a lot of stuff in Snowflake that happens in the background that we like to do automatically, right? And not have the user worry about. And a common question we often get is, well, clustering just sounds like sorting data, right? It sounds like just you're running a bunch of order by statements. And the question, which is a really good one, is, well, why can't we just do this on our own? Why do we need to use automatic clustering? And our answer to that is, well, you absolutely could do that on your own, and you would achieve the same outcome as automatic clustering if you ran a bunch of order by statements on your own to go and sort the data by your given clustering key. The advantage of using automatic clustering, of course, is that this is something that's done automatically, and it's done in the background and doesn't affect, for instance, write performance, write availability. There's no locks on your data or anything like that you need to worry about. While if you were doing a bunch of order by statements that you were manually running, you might encounter a lot of those challenges. But of course, if you needed to, let's say, sort a bunch of data, right? Think of clustering and order by as similar ways to achieve that. Of course, the advantage of clustering is that it's automatic and it can be done online without impacting your workload's performance.
Gotcha. And also, I guess the kind of fringe benefits of doing clustering is that you get the resized micro partitions and other things, which you want
Bingo.
to do doing.
Another great point. I forgot to mention that. Exactly right. Yeah, that's another huge benefit.
Awesome. So this was fantastic. I was thinking maybe it's time to show a demo of how one can actually enable automatic clustering on a table and see how that helps.
Yeah. So I can show you the statement. Enabling clustering is easy. So I won't cover that in a demo. It's almost like watching paint dry. It's such a simple thing. All you do is run this SQL statement here, right? You alter the table and then specify your clustering key. And honestly, that's the easy part. The exciting and interesting part is once you've enabled clustering, going and analyzing the impact on cost and performance. And like we talked a little bit about earlier, you benefit from clustering if lots of your queries are able to prune data as a result of your clustering key. And it's a feature that will improve performance, right, for those queries if we're able to prune micro-partitions and scan less data. Now, what I pulled up here is a query that uses our new table pruning history account usage view. This is a view that shows you at the table level. And I'll actually zoom in on this so you can see it even better. It shows you at the table level pruning per hour for each of your tables. And what I've done is I've joined that with this tables account usage view, and I've joined on the table ID to join these together. And then what this will show me is on each of these tables, first off, it'll show me the table ID, the total number of micro-partitions scanned, the pruning percentage, and I get the pruning percentage by dividing partitions scanned over partitions pruned rather over partitions scanned plus partitions pruned together. The percentage gives me a good idea of am I scanning all of the data in these tables every time I access them, or am I pruning a good amount of the data away when I access them? What I'll do is I'll make this a bit bigger so you can see the bottom. I sorted the results of this by, in descending order, the tables in our internal Snowflake account, which we call Snowhouse. I sorted them by total partition scanned. So you can see that this table here, table ID 77318, has, I don't know how many digits that is, I think about 700 billion micro-partitions scanned per week, right? So it's obviously a ton. But this table, we're able to prune 77% of them because we're using automatic clustering. We've clustered on these particular columns here. We've clustered on the hour. We've truncated, created on, and we're using the hour value to cluster by this table, and so on. And we can see the other tables that we've clustered by internally, and we can see how many micro-partitions we're able to prune on those tables over time by clustering those values. Now, obviously, if you see tables with pretty poor pruning or automatic clustering isn't enabled, these are potential candidates, right, for clustering in the future. It shows that we're pruning very little data in these tables and scanning a lot of data. So perhaps this is something where we could use features like automatic clustering to go and improve performance and therefore improve pruning. Doesn't mean that for sure automatic clustering would help, but it could be something that's worth looking a little deeper into and understanding the workload more.
Got it. And just a quick question here. So in the pruning percentage column that I see, it's naturally the number of partitions pruned to the total number of partitions scanned and pruned, which means I want that percentage to be as closer to 1 as possible for an optimal scenario. But
exactly.
What does it mean when I look at the rows 2 and 4, when I see the pruning percentage is so low? How do I go from here?
Yeah.
What does it mean to the...
That's a great question. So if you see that the pruning percentage is really high, that's a signal that you're getting a lot of value from automatic clustering. Of course, if the pruning percentage is lower, that means that you're not pruning very many micro-partitions. So you want to take a closer look at, did you pick the perfect clustering key for your workload? And then, of course, also, is clustering worth it? If you're only pruning a small percentage of micro-partitions and clustering is expensive, it might not actually be giving you really a meaningful benefit. Of course, it's also possible you might have just clustered by the wrong keys. So if you see that here, as we see in rows 2 and 4, that maybe be a signal that's something to look a little deeper into.
Got it. So that's very helpful too. So it's not just a one-time thing where you just created create this new key and cluster by this new key, but also a way for us to kind of dive deep into see how helpful has it been for us, maybe, re-examine the keys that we've decided to use and all that.
Exactly. Yeah, it's super helpful for that. Then we have this other new view here called table DML history that helps you understand a bit about why your clustering costs were what they were. So for clustering, you benefit when you have queries that go and access the cluster tables and you get better pruning. And the more the cluster tables change over time, the more you pay to maintain automatic clustering. So what this new account usage view, which is newly generally available, shows is for each of your tables, how many micro-partitions, or how many rows rather, were added and removed over time. And that'll give you a sense of what drove the high automatic clustering costs. So what I've done here is I've joined that view with automatic clustering history view, and that gives you basically your automatic clustering costs over time. And I've gone and sorted by automatic clustering costs. So basically then what we have here is the top 5 most expensive cluster tables internally within Snowflake. And obviously these are huge numbers, right? Because our internal users of Snowflake is enormous. So it's not typical for costs to be anywhere near this high. But in these specific cases, we can see that the cost was really high because we had, I don't know how many digits that is, but literally like trillions or quintillions, a very big number of rows added. So it helps give a sense of, okay, for these tables, what was driving that high cost? And then of course, this is very similar data that we also use to estimate your automatic clustering costs. And when we showed that earlier, we use a lot of this information about how many rows you would have needed to add and remove. And we try to predict that to understand what your automatic clustering costs would be.
I think this is also very good, interesting data point for me, because when I thought about automatic clustering, I only thought of the absurd use cases where, oh, my table is going to get new rows added to it, and then Snowflake will automatically cluster it under the new key. Looking at this one, even if I'm removing or deleting some of the rows, it would still have to do the clustering under the hood all over again too. So.
Yeah, in general, that's a great point. Anytime you're adding or removing data, we're going to do work in the background to maintain the data in a well-clustered state. I'd say in general, updates are the most expensive thing, but that's just a very general rule. Obviously, it's very situation dependent, but in general, updates tend to be the most expensive to maintain.
Gotcha. Fair enough. This was very cool. Thank you so much for showing a good way for us to kind of dive deep into how to better look at what keys you should cluster on and how to look at the table history and the query history to also understand where the cost might be coming from. I feel like maybe it's time to take some questions from the audience. Let's give 5 more minutes for questions.
Sounds great.
I know we're well over time, but we'll take a couple questions before we log off. All right. So I think there is a relation of automatic clustering with migration of streaming API temporary format into U partitions. This is all Greek and Latin to me. So is there a relation to automatic clustering with migration of streaming APIs into U partitions?
I'm not sure I understand that question. There could be maybe additional context there.
Yeah. I feel like it's probably a streaming question too, not necessarily within the context of what we're talking about with automatic clustering today. But I guess the tangent of this potentially is coming from like Snowpipe and the Snowpipe streaming side of the world. So we could get to them later on this.
Yeah, certainly.
All right. Okay. So I think with that, maybe let's wrap up. I know we're well 10 minutes over the planned time. Or first things first, thanks everyone for tuning in from different parts of the world. I do have one big CDA. I know Tim went over a couple of blogs and references to show you and how to use clustering and really what's the best practices around clustering. We will make sure to send over those list of blogs in the comments. Feel free to refer to them. And yeah, so that's pretty much it. Thank you so much. And thanks, Tim. This was a very informative session for us.
Thanks again. It's great to see you again and talk to everyone.
Mm-hmm. Bye-bye.